All right, let's jump straight into this explainer and unlock some seriously elegant mathematical shortcuts. If you've ever found yourself totally bogged down by pages of algebraic long division, staring at some massive cubic equation and thinking, there has to be a faster way to do this, well, you are in the exact right place. Today, we're going to master the factor and remainder theorems. But to truly appreciate these modern math hacks, we actually need to start way back with an ancient quest for the unknown. So before we even touch complex algebra or polynomials, take a look at the abacus. This was a brilliant physical calculator that grew out of the Han Dynasty's early number systems. It literally paved the way for solving complex numerical puzzles centuries before anyone was scribbling variables like x and y on a piece of paper. It's a great reminder of humanity's deep-rooted, almost instinctual desire to calculate, divide, and figure out what remains. And that desire brings us perfectly to this specific riddle from the ancient Chinese mathematician Sun Tzu. He posed this problem over 2.5 millennia ago. He's basically asking us to find a completely unknown number based entirely on its remainders after division. It's crazy to think about, but this riddle is actually the historical forerunner to the modern theorems we're exploring today. Sun Tzu was playing with remainders, and as we're going to see, remainders are the secret key to unlocking complex algebra.
Okay, here's our roadmap for this explainer. We'll quickly cover the polynomial puzzle, roots and graphs, the long way, our two shortcuts, the factor and remainder theorems, and finally, we'll face the boss battle.
So Section 1, the polynomial puzzle. Let's just define our terms really quick so we're all on the same page. Polynomials are simply mathematical expressions categorized by their highest power, which we call the order. Now, you're likely already super familiar with quadratics, right? Where the highest power is x squared. But today, our main targets are cubic expressions, equations featuring an x-cubed term. And as you might guess, when you bump up the power, the complexity of actually finding the solution bumps up right along with it. Moving on to Section 2, roots and graphs, visualizing the solution. The absolutely crucial point here is what we mean by a root. When a math problem asks you to solve a polynomial or find its roots, it's really asking for a very specific geographical location on a graph. Finding a root just means finding the exact spots where our curve hits 0 on the y-axis. It's literally that moment the line crosses the horizontal x-axis. Let's look at this in practice. If we map out the coordinates for this specific cubic equation, y equals x cubed minus 5x squared plus 2x plus 8, we get this table of values. If you scan that bottom row looking for the zeros, boom, there they are. The exact roots appear cleanly at x equals -1, x equals 2, and x equals 4. If you drew this out, the curve would perfectly slice through the x-axis at those 3 exact coordinates. But here's the catch, right? We don't always have the time or the graph paper to draw a curve and manually hunt for zeros. Which brings us to Section 3, the long way, algebraic long division. Finding those roots algebraically usually means taking a massive cubic equation and dividing it by a smaller linear factor. You could do algebraic long division, carrying down terms, subtracting lines of equations, or you could try comparing coefficients. But let's be totally honest here, both of those traditional methods are exhausting. They require so many tedious steps where dropping just one tiny negative sign ruins your entire page of work. It's a nightmare. So Section 4, Shortcut 1, the factor theorem. We are bypassing the long division entirely. This theorem is a total game changer. Read it carefully. It basically says that if you have a polynomial function, let's call it f of x, and you suspect that x minus a might divide into it perfectly, you do not need to do the long division. You literally just take that value a, plug it into your original equation wherever there's an x, and do the basic arithmetic. If your final answer is exactly 0, congratulations, you just proved it's a perfect factor. Let's see how efficient this is in action. Say we get this cubic equation, x cubed minus x squared minus 10x plus 12. Instead of setting up a massive division bracket, we just test a number. Let's substitute 3 into the equation. 3 cubed is 27, minus 3 squared, which is 9, minus 10 times 3 is 30, plus 12. So 27 minus 9 minus 30 plus 12 equals exactly 0. Bam! By simply substituting 3 and hitting 0, we immediately isolate x minus 3 as a linear factor without writing a single line of long division. It really does feel like magic. But wait, what if it doesn't divide perfectly? Section 5, Shortcut 2, the remainder theorem. Finding the leftovers. Look at this side by side. If you contrast the heavy lifting of traditional long division on the left, full of brackets, cascading subtractions, and endless chances to make a careless error, against our next shortcut on the right, well, the winner is incredibly obvious, isn't it? What's really cool is how the remainder theorem just naturally generalizes our last rule. It says that if you take your divisor, x minus a, and substitute a into the polynomial, the resulting number isn't just some random output. If it's 0, like we saw, it's a perfect factor. But if substituting a number doesn't give us 0, whatever number it does spit out is exactly the remainder. No long division required to find your leftovers. Let's try it out. We need to find the remainder when this messy cubic polynomial is divided by x minus 2. Using the remainder theorem, we literally just substitute x equals 2 into the equation. So 2 cubed is 8, 2 times 2 squared is another 8, minus 3 times 2 is minus 6, then minus 5, right? So 8 plus 8 minus 6 minus 5 equals 5. In just 3 quick mental steps, we found our remainder is 5, saving us minutes of nasty algebraic manipulation. It is so satisfying. All right, section 6, the boss battle. Let's conquer the exam. Now, here is the real beast. We're looking at a classic Cambridge exam-style cubic equation. But look closely. 2 of the coefficients, a and b, are completely missing. The problem is, f of x equals a times x cubed minus 15x squared plus b times x minus 2. How on earth do we find a and b? Well, the exam kindly gives us 2 distinct clues. Clue 1, the equation has a perfect factor of 2x minus 1. Clue 2, it leaves a remainder of 5 when divided by x minus 1. This is exactly where we deploy our hacks. By applying the factor theorem to that first clue, we know that if 2x minus 1 is a factor, substituting x equals 0.5 into the equation absolutely must equal 0. That's our first equation. Then we apply the remainder theorem to the second clue. Substituting x equals 1 into the equation will equal exactly 5. That generates our second equation. Just like that, you have 2 simple simultaneous equations. You solve them together, and boom, you prove that b equals 8, and you easily figure out the value for a. What looked like an impossible puzzle is entirely dismantled by our 2 theorems. Which brings us full circle, doesn't it? Sun T figured out his complex remainder puzzle over 2.5 millennia ago, relying entirely on mental arithmetic and pure logical deduction, without any of these modern algebraic tools. It really makes you stop and wonder just how far human ingenuity can stretch. If an ancient mathematical pioneer was handed the factor and remainder theorems today, what incredible unsolved problems could he conquer next? And honestly, more importantly, now that you have these tools in your own exam strategy toolkit, what will you solve?